Hello, welcome back to Hidden in the Stars. This week we're covering our first submission idea, Gravastars. Thanks to Jeff for the wonderful and very interesting topic. We learned some cool new things researching this one. Come along with us as we discuss a mystery puzzling astrophysicists for over 100 years. You may ask, why are gravastars such a mystery? Well, they haven't actually been proven. Yet. They are theoretical objects that are alternatives to black holes. What in the world could an alternative to a black hole be? A white hole? Something that lets all light escape? Wouldn't that be a star? First, let's understand black holes.
A black hole is a cosmic body of extremely intense gravity from which nothing can escape. Absolutely nothing, not even light. Black holes are formed by the death of massive stars like neutron stars. We'll cover massive stars in another episode. To die, a star must use up all its fuel inside its core. This causes the core to become extremely unstable, and it gravitationally collapses inward upon itself as it expels its outer layers out into the universe. That's a lot to take in. So, what does that all really mean?
Gravastars are different from black holes in a few important ways. Gravastars don't have a singularity in their cores. Black holes do. Gravastars don't have an event horizon. This is very important, perhaps the most important. Gravastars have a very thin shell of what we call ordinary baryonic matter that connects the de Sitter spacetime inside to the Schwarzschild geometry outside. You may be familiar with the name Schwarzschild from the concept of the Schwarzschild radius. Finally, gravastars are not made up of the same energy as black holes. Instead, they are made up of super awesome exotic matter.
Let's break that down even further. What's a singularity? A singularity is when the weight of elemental matter collapses in from all sides, all angles gravitationally in those dying stars we're talking about. It compresses them down so small that they have absolutely no volume, zero volume, and infinite density. Hard to imagine, but this is what a singularity is. Gravastars don't have this in their cores. Remember, we said that black holes do. Think about that infinite density.
Next, we mentioned the very important event horizon. Going back to black holes, an event horizon is like the boundary or the edge of no return around a black hole where the gravitational pull is so strong that, once again, nothing, not even light, can escape it once it gets to that distance, to that horizon. At this event horizon, an interesting astronomical anomaly occurs. The escape velocity, which is the slowest velocity some object must have to escape the gravitational pull of another object, in this case, the case of the black hole, is faster than the speed of light. I'll repeat that. Faster than the speed of light. Do we know anything else faster than the speed of light? Haven't we heard the only thing faster than the speed of light was the initial expansion of the universe at the time of the Big Bang? Now, all of a sudden, we have to understand this thin shell concept. Theoretical astronomy can be hard. Well, not really. Never fear, your friendly YouTube astronomer is here. When we say thin shell, astronomers really just mean a thin layer of liquid that separates the inside and outside regions of the gravastar. The thin shell prevents the formation of an event horizon, avoiding the infinite blue shift. Blue shifts and red shifts will be the topic of another enticing episode having to do with distances and why we can actually see the things we do in space. This thin shell made of fluid is balanced where the pressure inside is equal to the energy density. Also, outside is true vacuum of space where the pressure is equal to the energy density, which is equal to zero. This is knowledge for all you astrophysicists and chemists out there. So delicate. Inside is dark energy-like behavior. This is why it doesn't collapse to a singularity. Maybe we should summarize what we know so far.
Gravastars are alternatives to black holes. They have four main points that differ. We've learned two and a half so far. Black holes have a singularity, an infinitely dense point of zero volume caused by the gravitational collapse of massive stars. But gravastars do not, because of the dark energy-like behavior on the inside of the thin shell. Black holes have an event horizon, a distance from which nothing, not even light, can escape its gravitational pull. Gravastars do not because of the thin shell. This thin shell is just a layer of liquid separating the outside of the gravastar from the inside. Not so bad. Seems like we just need to remember that the shell is important in the structure of the gravastar. 1.5 points to go, and it'll all make sense.
De Sitter spacetime? As mentioned, gravastars have de Sitter spacetime as interior and exterior Schwarzschild geometry, while black holes usually have exterior spacetime like Schwarzschild. So it's backwards. Okay, but what does this mean? More weird names. It just means a theoretical spacetime geometry and general relativity characterized by positive cosmological constant. Easy, just break it down. Theoretical space-time geometry proposed shapes in space. In general relativity, Einstein. Last, a positive cosmological constant refers to the shape of the universe. In this case, positive would make it rounded like a sphere. So overall, it refers to an accelerating rate of expansion, positive curvature of space, and including dark energy. Last hard topic, then an easy one. Schwarzschild? Schwarzschild is a familiar name when thinking about black holes, hopefully. You may recognize it or recall Schwarzschild radius. It's a term referring to the distance from the center of a non rotating black hole to the event horizon. Schwarzschild geometry refers to the geometry of empty space surrounding a non rotating spherical mass. It describes the space time outside of a massive object. It's a simple solution to Einstein's field equations. It was discovered in 1915 by Carl Schwarzschild after Albert Einstein published his paper on general relativity.
Finally, something simpler. Exotic matter is awesome. Exotic matter is just matter that behaves rather oddly. It can be created in labs by cooling materials to very, very low temperatures. Some examples of exotic matter are dark matter, strange matter, and superfluids. Dark matter makes up the majority of the universe. Strange matter is found in the cores of neutron stars. Superfluids are liquids that can climb up walls. They defy gravity. Some fun properties of exotic matter are that they can have negative energy, which means they have negative mass. They can be created by putting baryonic matter under high pressure, and sometimes the properties are uncommon, even rare. If they're theoretical, then who possibly thought them up? This all seems rather complicated to be some sort of hypothetical. Well, in 2001, Pavel Mazur and Emil Motola proposed the idea of gravastars. The word gravastar is a combination of the words gravitational and vacuum star. They're thought to be cold, dark, compact objects. They're thought to be made up of three regions: the interior, the thin shell, and the exterior. They were thought up as solutions to Einstein's field equations. So they didn't just appear out of thin air. They did have a reason for being thought up, a very meticulous reason.
They're currently being studied by astrophysicists worldwide, with a super cool new theory having arisen. The latest theory involving gravastars is like Russian nesting dolls, where it suggested that they could be nested inside one another with multiple existing inside each other. This could potentially create a complex structure that could be possibly detected through gravitational wave signals. This is being called a nest star. Gravastars are very hard to understand until you break down the individual concepts. Perhaps one day even LIGO will detect gravastars. Until then, we'll just have to wonder. Thank you for tuning in to this slightly more complicated episode on gravastars, an alternative to black holes. What do you want to learn more about next? Leave a comment below. Tag along and join us on our journey through the cosmos. Catch you next time on Hidden in the Stars.